So in preparation for our discussion tomorrow, we're going to look at really quickly some complex splitting patterns in NMR. And let me just say off the bat that this is not meant to be exhaustive. There are volumes and volumes of books that discuss this particular topic, but I just want to touch on a couple of things, namely complex splitting as it relates to like AMX type systems, complex splitting as it relates to diastereotopic protons. Let's look at the rules quickly for spin-spin splitting. One of the first things to note is that if protons are equivalent, then they won't split one another. And so this is an example of these three protons. They're all chemically equivalent, so they're not going to split. Here, because this molecule is symmetrical, these protons won't split each other either, so they all show up as one signal. When protons do split, they're on adjacent carbons. So here's a carbon next to it, and the hydrogens on those carbons will feel each other's magnetic field. And so when that happens, that's when they split one another. And so you would definitely see splitting here. In this case, the protons are more than 2 carbons apart, so there's not going to be any splitting here. Here, what you would see is the signals being split into n+1 peaks, where n is the number of neighboring protons. All right, so let's just say, for instance, for this carbon, it has one neighbor here, and so this will be split into n+1 number of peaks, where n is 1 because of this one neighboring proton. And so the signal is going to be split into 2 lines, or what we call a doublet. All right, so ethyl acetate, let's take the n+1 rule and apply it here. All right, notice I have 3 signals, and the protons are color-coded, and the arrows are color-coded to those protons. All right, so this singlet right here, that's representative of these this red set of protons here. All right, if we use the n+1 rule, this should be a singlet because n is 0. What that means is that on this carbon there are no neighboring protons, and so if n is 0, n+1 is 1, so we get that to be a singlet. The blue set of protons has 2 neighbors, and because of that, n is 2, 2 + 1 is 3, so the blue set of protons is going to be represented by this triplet here. And you can see the signal split into 3 lines. Down here we have a quartet, or a signal that's split into 4 lines, and notice this is the pink arrows is representative of these pink protons, so this signal here is for the pink protons here. All right, so I have 3 neighbors here, no neighbors here, and so what that means is that that signal is going to be split into a quartet. N would be 3, 3 + 1 is 4. All right, so now let's look at a little bit more complex example. Right, you can see that the teal protons here would be split by this one proton, and that would be a doublet, which we have here. All right, I'm just zooming in on these areas. This is a pentet here, and it's representative of this red proton. It has 3 neighbors on this side. It has 1 neighbor here, so n is 4, and then n+1 would be 5. So the signal is split into a pentet. All right, when we get down here in the alkene region, looking at the pink and the green protons, you'll notice the green proton, the splitting pattern is normal. It has 1 neighbor here, and so it's going to split into a doublet, which you see here. But the pink proton is a little bit different, and the pink proton looks like 2 doublets together instead of what we would expect to be a triplet, because this proton splits here and this one splits here. And so what we see for the pink proton is what we call a complex splitting pattern. This pink proton is actually going to see the red proton and the green proton separately. All right, so that's what we call complex splitting. That's why you see the signal being split like this. And so that splitting pattern is what we call a doublet of doublets. And so we're going to talk more about that in a second. And then this is just a zoom of the aromatic region. But let's talk more about that doublet of doublets. So that's complex first order splitting. It happens when you have what's called multiple non-equivalents. So an example of this is here, styrene, right, where all 3 of these protons are non-equivalent. When that's the case, then what ends up happening is that each one of these protons will be able to split with each other, right? And so here, this proton is going to split with X and with M, right? We call that type of system an AMX, right? This HX is going to split with A and with M, right? And then M would split with A and with X, and so each one of these is going to have its own unique splitting pattern. You also observe complex splitting when you have diastereotopic protons. These are considered diastereotopic here, and the reason is because they're adjacent to a chiral center. So we're going to talk about that in just a minute. All right, still following the n+1 rule, where your signals are going to be split into n+1 number of peaks, but the splitting now again is a little bit more complex. So let's look at the splitting for styrene. Okay, so here's styrene, and then here is the Proton Nmr. And what you'll notice is that here, these two signals again look like two doublets side by side. Here we look like two doublets side by side, and then HA, the proton, is also it looks like two doublets side by side. It's tempting to call this a quartet, but remember, with the quartet, the two outer peaks on the signal will have the same height, and then the two inner peaks on the signal will have the same height. And so because they don't, you can readily see that this is not just a regular quartet. So how is it that this splitting happens? Okay, so let's take HA for instance. HA is going to split here with HX, and it's also going to split here with HM. Well, HX is one neighbor, and so if I apply the n+1 rule, the signal for HA should be split into a doublet for HX and also a doublet for HM. So we call this type of splitting pattern again a doublet of doublets. And then if you look at HM, it's the same thing, right? It's going to split with HX and it's going to split with HA, and you can see that these are two doublets here, right? This is a doublet and that's a doublet, so we'll call it a doublet of doublets, and it's the same thing for HX. So how do we arrive at this? It helps to use what we call a splitting tree. This is a generic example here where A is whatever my proton signal is, and then whatever that signal is split into is here. So if A is split into a doublet, then that's these two lines here, right? And then if that doublet is split again into another doublet, then we have 4 lines here. So each one of these lines in the doublet is also split into a doublet. So that's how we arrive at the doublet of doublets. So let's look at styrene again, right? So for A, HA, which is here, right? HA is going to couple with HB here, right? And so we see this is just a signal without any splitting, but when it couples with HB, it splits here. So you see a doublet, and then that doublet, because HA can also couple with HC, is also going to be split into a doublet. So now instead of seeing 2 lines, now you're going to see 4 lines. And so this is where the whole idea of a doublet of doublets comes from. And you can see the distance between the peaks. We call that the coupling constant, or the J value, right? Over here, this is for HB, and again, HB is going to couple with HA, and so we see the coupling here. It should be a doublet because A is 1 proton and n+1 is 2, so this should be a doublet. And then when it couples with HC, we should also see a doublet. So again, the signal for HB is going to be split into a doublet of doublets. And so I hope that helps, and if you have questions about it, you can always ask during class. Last thing I want to talk about is the diastereotopic protons, and I showed you an example earlier. So this is a chiral center, and we have 2 protons adjacent to it, and we call these protons diastereotopic because if I replace either one of these with another atom, so if I replace the pink hydrogen with another atom or the green hydrogen with another atom, then I get 2 diastereomers because of that chiral center that's already present. And so with that being said, these diastereotopic protons are non-equivalent, right? They're not equivalent to one another because of the chiral center, and so because of that, they split not only with the adjacent proton here, but they also split with each other. So the pink signal, which is shown here, again, if you look at the splitting pattern, you would expect this to be a simple doublet, but because it's not equivalent to this one, that's also going to split it into a doublet. And so for this pink proton, we see again that doublet of doublets type pattern, and then for the green proton, we see a doublet of doublet type pattern. And so the 3D model over here, here's the green proton, here's the pink proton, here's the red proton that's actually on the chiral center. And so that's going to, the red and the green are going to couple. That's going to give me a doublet. And then the red and the pink would also couple, right? And that'll give me a doublet. And so because of that chiral center, these two protons are not equivalent. They're diastereotopic. Each of them will give its own signal, and also they will split one another. So not only do they split with the neighboring protons, they also split with one another. So I hope this helps. If you have any questions, ask me in class tomorrow, because we're going to work on this. All right, thanks.